My name is Daniel Demmler, and this is joint work with Thomas Schneider and Michael Zohner. And it's a little bit about Android, so that's why I chose this thing. So thank you for coming, despite the quite unsexy title of our work. So, but let me walk you through what the title is about. So Ad-Hoc secure two-party computation on mobile devices using hardware tokens. Ad-Hoc means efficient and decentralized, so we want to do on-the-spot communication and computation without relying on the internet, and we want to do it in a practical way, essentially. And secure computation allows us to do it to preserve the privacy of the inputs that we put into the computation, and we do it on mobile devices, obviously. And we make use of hardware tokens in order to make it secure and fast. Okay, so why did we do it on smartphones? Because they're awesome, right? You can do all sorts of things with them. You have your contacts on them, you have your calendar on them, you have location-based services, all sorts of things you can do with that. People do their banking with it. You can do messaging, you can play games. And there's a couple of more things that you can do with your phone. But also, smartphones are limited compared to desktop computers. They're not exactly fast. For example, you don't have an AES instruction set. So yeah, there are some limitations to the computation speed and power. You have limited memory. The communication is rather slow because it's wireless, so you have a delay. And the throughput is not as good as an Ethernet through Ethernet cable or fiber or whatever. And the most limiting factor is the battery life. So if you try to do some fancy computations, you'll run out of power rather quickly. And since you want to be mobile, you don't want to plug it into the wall all the time, right? So what we want to do is we want to use all those functionalities, and we want to be mobile, and we want to make use of the amazing things we can do. But on the other hand, we want to keep our data safe. We want to keep it private, and we don't want to reveal much information, and at least not more than we really have to. So that's where secure computation comes in. To be more specific, generic secure computation, that means you can essentially do every function that you want, and you can represent it as a Boolean circuit. So that's the function that we want to evaluate. We do it in a two-party scenario. There is also work with multiple parties, but we limit it to two parties, Alice and Bob. And they each has a private input, and that can be contacts, that can be dates, or that can be essentially everything, but they want to keep their inputs private to the other party. And we are in a passive adversary model, so we exclude active attacks. And that can be applied if you're on a business phone, if you have software attestation, or just to evaluate how quick secure computation actually can get on devices. So it's maybe not the most realistic assumption, but it serves our purpose for now, and we look into extending it to active security in future work, obviously. So where did secure computation come from? Essentially, it's a rather old field. It's like almost 30 years that Yao came up with garbled circuits, and there's the protocol of GMW that we actually use. But they are rather inefficient, so you need to do a lot of symmetric crypto, and you need to do a lot of communication, and this is not really possible on mobile devices. So interestingly, there are a number of papers that were also presented on USENIX. Exactly 10 years ago, Fairplay, I think it got the best paper or best student paper award. So they came up with the first implementation of Yao's garbled circuits. And Huang et al., they proposed FastGC 3 years ago, also at USENIX. I think it was HotSec. And also Huang, Carter, and Evans, they implemented Yao on mobile phones also 3 years ago at USENIX. But they were not really practical. So, of course, they succeeded to do it, but if you look at the runtimes, then you get like a couple of hundreds or thousands of seconds, and you don't want to do that real in practice, right? Okay. So what are some applications for secure computation? If you've been in the session before lunch and have seen the private set intersection talk, then finding shared contacts is one of the applications that you can do with secure computation. So here we have Alice and Bob. They have their address books, and those are obviously phone numbers. And they want to find out which of their phone numbers match. So here it's like 10, 10, 10, and 23, 42, 01. And that's actually the result of the computation. So even though they put in all their address books, they only learn like the intersection of the function and don't reveal the rest of their address books. And another application is if you want to schedule a meeting, you sort of decide on a starting date and a period of time, and you just divide the time into slots. And actually what you compute is a bitwise AND. So you just set a 1 if you're available in that spot, and you set a 0 if you're not available, and out comes a list of dates where both are available, obviously. And you don't reveal what you actually put in. Again, it's in a passive adversary setting, so we disallow the attack to just input all ones, and then you get the result, right? Okay, and the third application that we considered in our paper is scheduling a meeting while also looking at location information. We did that to demonstrate that you can actually compute arbitrary information. So what we do here is you have a location information in your calendar, and N stands for next and P stands for previous. And you move from one spot to the other, and you have a radius in which you can move depending on how much time you have. And you actually want to calculate if you can physically meet somewhere. So here, for example, Bob goes from the shopping mall to the USENIX conference, and Alice is at the seaport village out there and wants to visit the aircraft carrier. And as you can see in the picture, they have some time and the location fits, so they can meet somewhere in front of the hotel and have their meeting without actually releasing information about their locations or if they are available or not. Right. Okay, so how did we do that? How did we envision that? We assume that our parties have a mobile phone and they communicate via Wi-Fi direct. So there's no third party that deals with the communication, and there's no internet involved. So it's direct communication between the parties. You could probably also do it via Bluetooth, but we haven't really checked that out, but I think that should be fine. And you can extend the whole setting with a smart card. That's where the actual performance comes from that makes the whole thing practical. And the smart card is held by one of the two parties. We just assume that Alice has the smart card. And in order for Bob to communicate with the smart card, he has to establish a secure channel to the card, which we do. And I'll evaluate later how that works and how fast it is. Details are obviously in the paper. Okay, so the protocol that we use, I mentioned earlier, is the GMW Protocol. It's also rather old. It's from Goldreich-Micali Wigderson from 1987. And the basic idea is to share values. So it's an XOR-based secret sharing. And each value that comes up in the protocol is shared between the two parties so that they actually have to put their shares together to reconstruct what the plaintext value is. What you can do in that protocol is you can evaluate XOR gates locally, so that it's essentially for free, or at least incurs just a minor overhead. But if you want to evaluate AND gates, remember the function is a Boolean circuit, then you have to do some interaction, and that makes it slow and complicated because you have to send values back and forth. And it's not as easy as, of course, doing it locally. And you need to rely on some pre-computed data, which is called multiplication triples. So where do they come from? In the secure computation protocol, we, like traditionally, had two phases. The first one is the setup phase, where you actually pre-compute those multiplication triples. And this takes a long time. So you don't know your inputs yet, but you know an upper bound on the function size. And then you pre-compute these multiplication triples that you need to evaluate the AND gates. And after that, you can actually do the secure computation, which is rather quick, where you put in your inputs and you get the function result. So we thought we need to improve this because this requires interaction from the start to the end. And so we extended by an init phase. And what happens is that we shift the workload from the setup phase to the init phase. And the nice thing is we do this on the smart card. And the nice thing is we can do that at any time. We don't need to know our communication partner yet. So we can be at home, plug our phone into the wall, and just let it calculate whatever it wants. We don't care about it because we can do it at any time. And of course, the goal is to shift the workload there, so the actual computation that we need to do live and online with our partner gets minimized. It's actually a similar idea to the ORAM talk that we also saw in the previous session. Right. Okay, so multiplication triples. That's how they look. So that's basically correlated randomness. So you can choose 5 of those 6 values. Those are bits. You can choose 5 bits randomly and then just calculate the 6th one. And obviously, you should not share the whole 6 bits with either party. So the bits with an A go to Alice, and the bits with a B go to Bob, because otherwise the whole thing wouldn't be secure. And that's how we actually calculate them. So instead of choosing them like from def random or what, we pick 2 seeds and we throw them in a pseudorandom generator, and we generate the bits for Alice and the bits for Bob separately, and calculate the CA bits here in this case. And since our smart card, which we use, has very limited storage, we actually write them out to Alice, which has a lot more storage. And she just holds onto them until she actually needs it. And as soon as we meet Bob, the setup phase actually starts. And what happens then is that the seeds are transferred to both parties. Again, here Bob uses a secure channel, so Alice cannot spy on the seeds that get transferred to him. And they can then locally recalculate their shares of the multiplication triples, which they need to evaluate the AND gates. What happens if you don't know an upper bound in the function size? Well, then we came up with so-called multiplication triple sets. Essentially, those are just bunches of multiplication triples that come in sizes of powers of 2. So as soon as you know your function size, in this case x, you just need like a logarithmic amount of multiplication triples, and you can essentially construct any amount pretty efficiently by just transferring those logarithmic amount of seeds and extending them. Of course, in practice, you would use bigger numbers than 2, 4, and 8, but yeah, it's an example, right? That's how we design our application. As I said, it's on Android, and we already got this GND MSC service, which does the low-level communication with the smart card by the smart card vendor, and we extended it by the MTSet service, which takes care of this pre-computation, which runs in the background and checks if there are enough multiplication triple sets that are pre-computed. And on top of that is the actual secure computation app that does the protocol and the inputs and has a UI where you can pick what you want to do actually. Which I forgot to mention earlier is the blue part is essentially optional, so you can do secure computation without the smart card, but then you have to do the multiplication triple generation in the setup phase. So you have to do it while you met your partner and you have to wait for it to finish. So here's the hardware that we used. It's a Giesecke and Devrient mobile security card. It was publicly available in the last few years, but I guess it's sold out now. So I think you should find something similar, maybe from a different vendor. And just to give you some numbers to get an idea with what we're dealing here is like 75 kilobytes of memory and not even 2 kilobytes of RAM for an applet. And AES runs at a blazing amount of 16 kilobytes per second. So you're really limited in what you can do there. So you have to plan wisely, and you have to actually let it calculate for a few seconds ahead in order to, make use of it. And we used Samsung Galaxy S3 phones. I guess most of you are familiar with those pretty common phones. You actually have a quad core, so you can do some calculations on it, even though we don't really need the computation power that much. And of course, a lot of RAM and flash storage to store these multiplication triples. So if you calculate those if you calculate the multiplication triples via oblivious transfer, like interactively with the other party, then you actually manage to calculate 11,000 of them a second. I'll give you circuit sizes later on to get a feeling for how fast it is. And if you do it on the smart card before, then you actually achieve roughly half the speed. So it's the same order of magnitude, but just to give you the numbers here. And to come back to the applications, how fast are they actually in practice? So if we want to do scheduling for 1 week, which we divide in 15-minute slots from like 8 in the morning till 10 at night, then we end up with 392 time slots, and we can set the bit for each one of them. So to initialize the data, it's really quick because we only need 392 of those multiplication triples. and that takes not even a second, and the setup time here is essentially just used for establishing the secure channel from Bob to the smart card. This is most of the time, and the online time, you don't really notice it because it's just a bitwise and you can do it real quick. So the actual ad hoc time adds up from setup and online time and is 1.3 seconds. And of course, this is really practical, even though the previous work also was, of course, practical. I mean, 3.8 seconds is really fast. There was, no, sorry. Okay, location scheduling. So it's the same use case, but we enhance it with the location information. As you can see, the function size, so this is the amount of AND gates that you have to evaluate, is a lot bigger, and also the depth of the circuit. It gets a lot bigger, and the depth of the circuit also limits your performance because you can only evaluate one layer of the circuit at a time. So that's why the online time is a lot bigger than before. And also, since you need that many multiplication triples, you need 48 seconds to actually pre-compute the thing on the smart card. If you would do it interactively via oblivious transfer, you would need roughly half the time, so let's say 24 seconds. And that's, I don't know if you want to stand there for 24 seconds and wait for your computation to finish, but I guess 2.6 seconds is fine if you do it in practice. Since that's our use case, no one else has done it, so we don't have values to compare. But the common context thing is a common use case. And we did it with 512 contacts, which I guess is a reasonable number, maybe even a bit too much anyway. And we used 32 bits representations of the phone numbers, so we just truncated them at 32 bits, I guess. The circuit is even bigger than before, so you need a lot more time to initialize the multiplication triples. And as you can see from the values, you can do the whole computation in 4.5 seconds. And again, I think that is practical for the use case. And if you compare this with related work, the first thing here is done on mobile phones as well. You need 1,500 seconds. You don't want to stand there for half an hour and wait for the computation to finish, right? And the last row is actually done on desktop computers, and that actually shows that we can achieve similar performance like Huang and Evans and Katz did in 2012. All right, so to sum it all up, how do we compare with related work and with other protocols? We can do computations even if we don't know the function in the init phase, so that's why the pre-computation works in the first place. There are also other protocols that allow this, obviously. We have very low ad hoc communication because we only need to transfer the seeds. And also our computation is very low. Once you have expanded those multiplication triple sets, it's only XOR operations. You don't need crypto in the ad hoc phase, and that's the phase that really counts. Okay, to conclude, mobile secure computation is becoming practical with a little star on top if you have a smart card. So yeah, but we're on our way, right? And trusted hardware obviously enables this secure pre-computation that we require. Yeah, and to look ahead, what are we planning to do? We're looking into maybe extending the whole thing for active adversaries, where you use MEX to actually guarantee that the computation was done right and no one cheats. And we think of maybe using multiple hardware tokens because that might even give us a bigger advantage and make things more secure. Yeah, and that's it from my side. Thanks for your attention. If you have questions, go ahead. Thanks.
Great. Let's thank the speaker. So we've got time for maybe one or two questions.
If I were curious whether you had a particular entry in your address book, couldn't I add it to mine and use that as a way to find out if you had it in your address book?
Yeah, sure. You could do that.
So wouldn't someone who's going to go to the trouble to use garbled circuits and so on think that would be a big privacy threat, for this application?
Of course, it's a privacy threat. But as I said, we're in the passive adversary model, so you exclude those kinds of active attacks.
But why is it reasonable to exclude them? I mean, we got a particular app in front of us here.
Yeah, sure. So as I said, we do this kind of work to evaluate performance in the mobile domain, and we plan to extend it to active adversaries. So it's not really practical, like you would sell the product and then rely on the security, but it was more like an evaluation if it was actually possible to do something like that in the mobile domain.
Okay, thank you.
Thanks.
Last question.
Hi, Jason Perry from Rutgers. It was very intriguing that for this application at least, the GMW with pre-computation was faster even for two-party than the garbled circuits. Is that sort of an artifact of your setup, or do you think that can be the case in general?
That's a good question. I think I would have to look it up, but I guess what we really benefit from here is the pre-computation on the smart card, and that makes it so much faster. So I don't think you can do it in general, but it works not only, but it works mainly because of the smart card. But I think I would have to look that up. Thanks.
And as Matthew gets set up, let me ask one final question, which is, so given that this is in the passive adversary setting, what does it take to get to the active adversary setting, and how do you figure that will affect your performance?
So the performance would, of course, get a lot worse, obviously. And what you do is you add some kind of information theoretic max to the shares that you actually transfer, and you validate them. There are different approaches. There's, I think, Tiny Lego, or a protocol of from Aarhus guys. So we haven't really started looking into it in detail. There's in the paper, you can, in the full version at least, you can find a sketchy version of what we envisioned might be possible, but it's not really thought through. So it might not work in the end. It might. So we're looking into that.
Great.
But of course, it will degrade performance a lot. That's sure.
All right. Thanks, Daniel. Can we thank the speaker?